Welcome back to part 2 of lesson 16. We start with this theorem that is one of the main points of going to canonical form, and it's that a canonical form LP always has at least one extreme point if it is feasible. The intuition is that if solutions are over non-negative variables, then they're in what's called the non-negative orthant. Orthant is the higher dimensional word used instead of, say, quadrant. So it's the analog of quadrant in n dimensions. The idea of the proof is that no lines, and this is a geometric reason, it's that no lines, right, which extend infinitely in both directions, are contained in the feasible region. And it turns out that leads to the idea that an extreme point must exist. It's actually a very beautiful proof involving the linear algebra connection to the geometry. For more details, the technical details, please ask me about it, and I'm happy to provide them for you. So this is good. We're looking, if we can look at all LPs as canonical form LPs, then we know we're going to find an optimal solution using the methods we've discussed. The question then is, well, how do we convert things into a canonical form LP? I'm also going to note another part of this story, as I mentioned before, is that the canonical form LP is a simpler form to work with because it has all equality constraints over non-negative variables. That's going to have a big impact. But how do we do this? So let's suppose we had an inequality, a less than or equal to constraint. We add what's called a slack variable, and we do that as follows. We just take the first expression over here, and on the left-hand side, we rewrite it and then to that sum, I add a single slack variable, and I turn the constraint into an equality, and then the inequality goes into the fact that the slack variable is non-negative. It's called a slack variable because it picks up the difference. You know, if you take this expression and rewrite it, SI is just equal to the difference between BI and the previous sum. In a similar fashion, this is what we do with the inequality going the other way, greater or equal to constraint, except now, instead of adding a slack variable, we subtract a surplus variable. In either way, though, we're subtracting the non-negativity. And it's these non-negativities, the non-negativity enforces the original inequality. And I realized I made enforces look really weird, so let me just rewrite that. Okay, so we've added some variables. Now, the crucial mistake not to make is using too few variables. You need to use each inequality has its own slack for less than or equal to, or surplus if it's a greater or equal to variable. And that's the only place it should appear except for its non-negativity bound. Okay, so if you see S1 and it's part of an inequality, it better not be a part of any other inequality except for its non-negativity bound. So keep that in mind. That's a common mistake I've seen made quite a bit. All right, so the other thing we have to do is we have to assure so that handles all of the constraints, because any other constraints is an equality constraint. So now we have to ensure that all of our variables are non-negative. So we have non-positive variables. It turns out those aren't so bad. You can either create a new variable and just substitute and put a negative sign where you had the original variable and put the new variable, or you can just keep the variable but just flip the sign everywhere. So substitute minus xj for xj. And note that minus xj less than or equal to 0 is the same thing as xj greater or equal to 0, and that's why that works. Okay, so I'll do that on the next page when I do some examples. I think the most tricky thing is what I see students have the most problems with in general, is when we have an unrestricted free variable, and then we replace them with two variables. So the notion is that instead of, we replace xj with xj plus minus xj minus. Now I want to just make one other point. When we say substitute this everywhere, once you make the substitution, this should not be in the formulation anymore. Okay, the original xj better not be in the formulation at all. Okay, once you make the substitution, because the idea is that we don't want it there. It was free. It was not part of the canonical form. Now the question is why does this work? And the answer to that question is that any real number can be expressed as the difference of two non-negative numbers. So we have any real number. The notion here is that it's a free variable, and we need to replace it with non-negatives, and it turns out any free variable is the difference of two non-negatives. There's some deeper ideas here too, but let's just focus on that for now. Okay, so let's do a couple examples, and then I'm going to ask a couple questions on the assessment, but one of the questions is really going to be about a homework problem. So make sure you have your textbook. You're going to need your textbook for the assessment. So you'll have to email me if you still don't have access. Which you should have by now through VitalBooks if you have an internet connection. That's pretty reasonable. I think, yeah, but we can talk about that if you don't. Anyway, let's get on to the examples. So the first thing we want to look at is you consider the variables. So first step, look at variables. And then keep in mind any substitutions, right? Because you're either going to have to flip the sign on a non-positive variable, or you're going to have to replace the variable with a difference of two non-negatives. And the third, then you handle the constraints, adding surpluses and slacks as needed. Well, I'm going to or adding in quotes because you might be subtracting surpluses. But I mean, add the variables to the formulation. And you only need to do it as needed. Another common mistake is people add slacks and surpluses to every constraint. And of course, you should not do that for the equality constraint. And when we get to that part in the example, I'll show you what we do. All right, so we still have a maximized problem here. And we have 3x, x is non-negative, y is free. So this means we're going to replace y with y plus minus y minus. Okay, so it's 3x plus 8 Well, 8y plus minus y minus quantity is just 8y plus minus 8y minus. Okay, and it's subject to, well, it's x plus 4y plus minus 4y minus. Notice how that minus sign carries through. And it's a less than or equal to constraint, so I add S1, and that's equal to 20. Okay, then I have x plus y plus minus y minus, and it's a greater or equal to constraint, so I subtract out S2. I have to use a different variable for this different constraint. It's equal to 9, and now I have x, y plus, y minus. I have to put all these variables now get to be non-negative, and that's great. So now we have all equality constraints and then non-negative variables. Okay. Let's do another one. I look at these variables. They're all non-negative, except I do have a non-positive. So I know now I'm going to replace x1 with minus x1 wherever I see it. So here I have, instead of x1, it's minus x1, so it's minus 5x1 minus 2x2 plus 9x3. Those didn't need to be changed. They're both non-negative. The first constraint is equality constraint, so I don't need to add any surplus or slacks. If you do that, that's incorrect. So you should not be adding any slacks or surpluses for equality constraints. However, I do have to do this substitution. It's minus 3x1 plus x2 plus 4x3, and it equals 8. The second one is an inequality, so I have to do something. I'm going to have to add or subtract a dummy variable. Note that slacks and surpluses are also called dummy variables. That just means they're artificial variables. They're new variables. Not artificial, but they're just new variables. So here it's minus 2x1 plus 7x2 minus 6x3. It's a less than or equal to, so I add a slack. And I'll call this S2. You could have called it S1. That's completely fine. I called S2 because it's the second constraint. And that equals 4. And then I have all my variables, and there's 4 of them now, are non-negative. Okay, so just note S1 instead of S2 would be fine. I used S2 to indicate it is in the second constraint. And note also the equality constraint in the first constraint needed no slack or surplus. Okay, that concludes the lecture. Please read the assessment over. Again, you're going to need your textbook for it. I'm going to ask you to do some homework problems from this section and ask you some questions.